rational equations for x, there's no solving it until x is on the side by itself. Okay? Just like that, there's no solving for this x until it is out from under that cubed root. So what's the process? The process is very similar to what we just did. We isolate the radical. So we have isolated squares that had x within them and then taken square roots of both sides. Now we're just doing it the other way around. So whenever I get a problem like this, my first step is to isolate the radical. Well, the radical is literally the thing that has the root in it. This is a cubed root. So that means this 2 needs to go to the other side. I'm left with the cubed root. I lose the pen, I'm sorry, there we go. I'm left with the cubed root of 2x minus 4. It is equal to 2. Next step is raise each side to the power that matches the index. This is a cubed root, so to get rid of a cubed root, I need to raise this to the third power. Raise it to the third power. If I do it to the left, I have to do it to the right. When you raise a root to its matching power, you just get the radicand, which is what's under the radical. And on the right, 2 cubed is 8. And now it's a linear equation. Add 4 to both sides, and then divide by 2, and I find x is 6. And then you'll check that in the original. And it does check. All right, so I know you're right on the edge here at 2:15, so we'll stop there. Any questions? I saw, Tinny, you said you were a little confused, but you didn't finish up. Is there anything you wanted to ask before we call it a day? And if you don't have time now, you can always shoot me an email. Everybody still here? Everybody okay? Had my camera off the whole time. Okay. I gotcha. All right. So next class, we're going to tackle the rest of the R5 and then hopefully get into R6. Don't worry about, the only due date you got to worry about is that R4 homework is due tonight, and then R5 will be due next Tuesday to match up with you'll see me again before it's due. So just make sure that R4 is done if you wanted to deal with that extra credit and get those objectives done as well. And if that's it, I will see everybody on Wednesday. That's not recording. What am I doing? Okay, there we go. So let me just repeat what I just said. Here we go. So if I do the math out here, that's going to be 9 plus, that's not big enough, 9 plus 112, all divided by 28, -3 plus or minus the square root of 121 over 28. 121 is a perfect square. Plus or minus 11 divided by 28. So this is going to bust up into 2 answers. I'm going to have -3 plus 11, which is 8 over 28, and -3 minus 11, which is -14 over 28. And do those simplify? Yes. Come here, mouse. Where'd you go? There you are. Oh, I hate how this thing just likes to hide on me. Yes. All right. So now, what does this do? 8 over 28 reduces to 4 over 14, which is 2 over 7. And -14 over 28 reduces to -1/2. Here's the trouble, though. because the directions were factor, these are not the answers. Okay? These are the values that if I take this quadratic and I factor it into two binomials and set them equal to 0, this is what I would get. So if positive 2/7 is one of the zeros, then that means this must have broken down into z minus 2/7 times z plus 1/2. And the reason is, if 2/7 is an answer, because remember, this one's not an equation, but we've used a quadratic formula. Now I'm just going to try to bounce back and make sure this makes sense. We've got to working backwards. If 2/7 is an answer, that means if I were to set the quadratic equal to 0, 2/7 would result in getting 0, right? So z is 2/7, 2/7 minus 2/7 is 0. So what do I have to do? Well, neither these reduces are going to be, so that denominator runs out front, and what I end up with is negative 7z over 2 times 2z plus 1 is equal to 0. You have never seen a problem done like that before, because I've never done one like that before. Okay, so this was just, I wanted to prove to you that quadratic always works. Is there an easier way? Yes, there is. And the easier way is you could do complete the square here, and that would factor. But for me, I just think that bottoms up process is easier to deal with. Bottoms up is just we're just taking the AC method and kind of making it our own. So in bottoms up, I take A and C and I multiply them, and that becomes my new value of C. 14 times -2 is -28. Does this factor? Yes, right? Two things multiply to -28 and add to +3. I am multiplying to a negative, so that means I know this is plus minus. And then two numbers that multiply to -28 and add to 3. That means my opposite signs, and then the sign that is dominant is positive. So whenever I find the two numbers that multiply to -28, the positive one is going to have the larger magnitude. Okay. Oh, that's why it does that. Just hurry pop. There we go. Yes. Mm-hmm. So then, yes. So, and here's the other thing. I haven't really thought too deeply about this, but I think it's right. Whenever I multiply to a negative and add to a positive or a negative, this number, this coefficient of B, tells me how many units apart the two numbers are. So I need two numbers that multiply to -28 and would add up to the difference between the two numbers is 3 units. And yes, 7 and -4 are not, they're more units than that, but 7 and 4, ignore the signs for a second, 7 and 4 are 3 units apart. So that's the idea. So there is, I've done this, that's not the right answer though, right? The right answer is down here. Well, remember I used bottoms up, and in bottoms up, I have to remember that I took that A and multiplied it by C. So now I have to come back and divide the numbers, the zeros that I found for the modified quadratic, and then I need to reduce. Can I z plus 17, 7 over 14 is 1/2, z minus, this looks familiar, doesn't it? And then neither fraction reduces to an integer, so this comes out to 2z plus 1, 7z minus 2. Are those the same? So there it is from bottoms up, and then you see the same thing here from the quadratic. But if you did this and you put equals 0 over there, it's going to be wrong. So be careful. because remember, it's all about what the question is asking, and in this case, the question only asks us, what the heck am I doing? The question only asks us to factor. It doesn't ask us to find zeros. All right. Anything else? All right. Okay. So that whenever I complete the notes, this will be the last page. And once we're back from break, I'm going to try and share this notebook file with you, because I know the PDFs that you are printing are in Smart Notebook, but I'm writing in the OneNote. So I'm going to see if I can share this notebook with you, and so that everything formats the same. The problems are the same. It just looks different, right? So what we did last time in R5, this is the second part. We're dealing with radical and absolute value equations, and I quickly ran through this and did an example, and I wanted you to remember the steps when you're dealing with radicals and those little, I just wrote it down. The rule here, or the easy steps to remember, are to isolate, exponentiate, and this is a little fancy, exponentiate, T-I-A-T-E, and liberate. Okay, isolate the square, exponentiate both sides, or isolate the radical, isolate the radical, get it on a side by itself, exponentiate, raise both sides to the power that makes the root go away, and then liberate is once you've done this process, once you have raised it to the power, then get x by itself. So it's almost like isolate, exponentiate, liberate, and then isolate again, but let's not think too hard about that. So step 1, isolate. Step 2, exponentiate. Step 3 is liberate. And this rundown is going to be the exact same for absolute values as well. So the one we did last time, I had a cubed root of 2x minus 4. Minus 2 is equal to 0. Step 1 is isolate, get it on a side by itself. Then I exponentiate both sides, and then I solve for the variable. On the right, I have my radical, my x minus 1 is equal to x minus 7. The isolate has already happened, right? The root is on a side by itself. Why do I need that to be the case? I'm going to do this one correctly, and then I'm going to show you what happens if you don't do this. So they've been isolated. Now I'm going to exponentiate. That's just fancy for raise both sides to the same power, right? No, we love nothing more than to sound smart in college, right? Now, when you start this problem, you think, oh, this is going to be easy. Yeah, look, they look like they're just two linear equations equal. This will be easy, and then this happens, right? When I square both sides, the right-hand side is x minus 7 squared. Please remember, that's x minus 7 times x minus 7, which is x squared minus 7x minus 7x is minus 14x. And then plus 49. Solve this. Well, this is a quadratic. So to solve it, I need to get everything on one side and then factor or use the quadratic formula, use a square root, whatever it takes. So that's x squared minus 15x plus 50. That looks like a 6 if I'm not careful. All right. So now I've got a quadratic equation, which just cracks so bad. I have a quadratic equation, and it's an equation because there's an equal sign. It's not a quadratic expression, it's a quadratic equation. And when I have the quadratic equation equals to 0, I try to factor it. Does this factor? Are there two numbers that multiply to positive 50 and add to negative 15? I promise you this is worth your time with the signs. I multiply to a positive and add to a negative. The only way that can happen is if both of these are negative numbers. Take the time to do that step, because now two numbers that multiply to 50 and add to negative 15, they both have to be negative. So that means they have to be negative 10 and negative 5. All right. Now, by the zero product principle, two things multiply to give me 0, then one of them is 0. And I can drop the parentheses. They're not necessary. Don't really mean anything. Or 0 is equal to x minus 5. Add 10 to both sides, x is 10. Add 5 to both sides, x is 5. And then we need to check, right? We've run into our extraneous solutions before, or we've already run into them in this class, so we want to check these really quick. So 10 and 5, the original is, I'm just going to copy it so I don't have to type it again. So I'm going to paste that and then indicate to the reader that I am checking. This is the original. So I'm checking x equals 10, and I'm checking x equals 5. If I do x is 10, that's the root. 10 minus 1 is equal to 10 minus 7. Square root of 10 minus 1 is 9. 10 minus 7 is 3. I only consider the primary root, which means the positive one, because it's just the square root of 9, which is 3. 3 and 3, that's fine. The only time you do that plus minus is if I'm taking the square root in order to move to the next step of the algebra, right? This one, it's just numbers. There's no variables in here, so I don't have to worry about that secondary. I don't have to worry about positive and negative 3 here. So that checks. So 10 is in the solution set. How about 5? 5 minus 1 is equal to 10 minus 5. No, try that again, Larry. X is 5. There we go. Square root of 5 minus 1. 5 minus 1 is 4. 5 minus 7 is negative 2. Square root of 4 is 2. Does 2 equal negative 2? No, it does not. So that means x equals 5 is an extraneous solution, so it's not included. So my solutions for this problem is just the number 10. All right, questions? Okay, I'm going to zoom out just a little bit because I want you to notice something. All right, so in this question, what is the new part? Okay, the new part, the thing that we are adding to this problem is done right here. I square both sides and then get everything on one side. Now it's just a quadratic equation. This is not new stuff. This is old stuff. All of the new is in these first two steps, really in the first step. Okay, everything else is algebra, and I'm calling back on the zero product principle here, and then I'm plugging values into a root. So just, I want you to take notice that it feels like, gosh, this is so much material, there's so many steps. Most of these steps are prior knowledge, okay? Most of these steps are not the new part that we're teaching, all right? So keep that in mind as you're doing it. All right, and then the last one, I was gonna show you, I'm gonna do an example on video of what happens if you don't, isolate the radical. So this needs solutions that are due. And then the last one here, here's our worst case scenario. And worst case scenario when you're dealing with radicals is that you have multiples. All right, the rules are still the same, but you just have to repeat the process. Okay, so I want to isolate, which means get one of the radicals by itself completely. Doesn't matter which one, I'm just going to get the square root of 2x minus 3 by itself. That means I need to add the square root of x plus 2 to both sides. That looks super weird to do that, doesn't it? How to add the square root of x plus 2 to both sides. Well, the square root of x plus 2 is just a number. I don't know what that number is because I have a variable in there, but it's just a number. So this is equal to 2 plus the square root of x plus 2. Now, remember, isolate this radical. The square root of 2x plus 3 is by itself. So next step is exponentiate. So I'm going to raise both sides. I need to raise it to the second power to get that radical to go away. But now here's why this is your worst case scenario. Because what have you created on the right-hand side? On the right-hand side, you've created 2 plus the square root of x plus 2 times 2 plus the square root of x plus 2. They're still binomials because it's just 2 terms. 2 is a term, and the square root of x plus 2 is a term. 2 is a term, square root of x plus 2 is a term. But when I FOIL this, what happens? First, life is good, that's a 4. Outer, 2 times the square root of x plus 2 is 2 square root x plus 2. Inner, 2 square root of x plus 2. And then last is the square root of x plus 2 times the square root of x plus 2, which is x plus 2. Combine like terms. And if you squint and close your eyes and hold it just right, you'll notice that this looks a lot like when we do this normally, right? When I FOILed on the right over here, that happened, or when I squared over here on the right, I ended up with double the middle term and then the square on the side. Same thing's happening here. 2 square roots of 2 plus 2 square roots of 2 is 4 square roots of 2. And I still have a root in here. So if you're looking at it thinking, oh God, what do I do next? Remember, my goal is to liberate that x out from under the root. Can I do any math on the right? Yeah, this 4 and 2 are alike. 4 plus 2 is 6. There's an x over here. And then there's the 4 square root x plus 2. Now, what am I doing? Let's pretend like we just started with this problem. What would I want to do? I would want to isolate the radical. So how do I do that? Well, I get it by itself. Subtract 6, subtract x. Straight lines elude me. There we go. And what happens? 2x minus x is x. 3 minus 6 is negative 3. 6 minus 6 is 0. X minus x is 0. 4 times root x plus 2. Is the radical by itself? Almost. Almost. I need to divide it by 4. I divide one side by 4, I have to do it to the other in order to retain equality. So that is x over 4, and I'm gonna split this up. The reason will become apparent in a minute. Let's just leave it, that's fine. x minus 3 all divided by 4 is equal to x plus 2. The radical is by itself. The only way to get rid of that radical is to exponentiate both sides. So what power do I raise both sides to? A second. Seems to be a theme, right? Squared. Squared. The square root is just what's under the root. And the square of a fraction, of a rational expression, is just the rational expression times itself equals x plus 2. Now, what happens over here? I've got two fractions multiplied by each other. So multiply the numerators, multiply the denominators. X minus 3 times x minus 3, that is x squared minus 6x plus 9. The denominator is 4 times 4, which is 16. Okay. And what do I have now? I have a quadratic. So how do I solve a quadratic? I get everything on one side. Minus 6x plus 9 all divided by 16 minus x minus 2 equals 0, because that was the next step. Subtract x from both sides, subtract 2. I can't subtract x or 2 from the 6x and the 9, negative 6x and the 9, because they're not like, they don't have the same denominator, so I need the same denominator. The denominator over here is 16, so these need to have a denominator of 16, which means I multiply both of them by 16 over 16. And why do that? Because I'll show this in a couple of steps. That's 16x over 16, and that's 32 over 16. Now that I have common denominators, I can put the entire problem in the numerator over the last few steps. Yes, minus 16x minus 32 over 16 equals 0. All right, last few steps. Let's take a look. And let's just finish it, and then I will step back in and we'll look at the steps. Negative 6x minus 16, well, that's painful. Negative 6x minus 16 is negative 22x. Positive 9 minus 32 is 23, and it's negative. All right. The numerator factors into two numbers multiplied negative 23, add to negative 22, that's negative 23 and 1. All right. Now, there's two ways to handle it from here. It's either get rid of the fraction by multiplying both sides by 16, or if you have a rational expression is equal to 0, the only thing that can make it 0 is the numerator. So you end up with x minus 23 times x plus 1 equals 0, and you know how to go from there. Now, steps, last few steps here. Okay, so scoot back. And, all right, this is the new part up here at the top. How did that go? That's okay, Sadie. I just assumed that you just hated me and math and just had to leave. But I'm kidding. All right. So these steps, these steps are good. This is what I expected to be the hard part, because that's all new. But then squaring both sides, I've got a radical on the left, or excuse me, I got a rational expression on the left, that radical on the right, divided by 4, I squared both sides. So I'm just repeating the process of what I did before. So x minus 3, quantity x minus 3 all divided by 4, quantity squared is just x minus 3 over 4 times x minus 3 over 4. Square the square root, multiply fractions, numerator, x minus 3 times x minus 3 gives me x squared minus 6x plus 9, right? And then 4 times 4 is 16. I now have a quadratic. And I tell you what, here, let's actually make life easier right here. Let me jump back. I'm gonna bring that stuff back, but let me choose a different path. So if I'm here, I'll divide by 16 minus x minus 2. Whenever you got rational equations, rational expressions, there's always two ways to handle them. You can either get everything on one side to have the same denominator, or you can clear the denominators. You do that by multiplying both sides by the LCD. The negative x, the negative 2 are all over 1, so they don't have anything to add to it. When I multiply by 16, x squared minus 6x plus 9 divided by 16 becomes just x squared minus 6x plus 9. 16 times x is negative 16x. 16 times negative 2 is negative 32. And now that I don't have a denominator, this probably makes a bit more sense. X squared, negative 6x minus 16 more is the negative 22x. 9 minus 32 is negative, I did it again, negative 23. Factored, minus 23 and plus 1. And look at that, even after all that work, what did I do? I worked my way so that I ended up with two things multiplied, two factors multiplied to give me 0. So 23 is equal to 0. X minus 23 is 0, x plus 1 is 0. Meaning I come out with positive 23 and negative 1. All right. The check is not as terrible as you would think it is. The real trick is going back and grabbing the original problem. So let me grab this so that we can put it down here. Did those steps help, Tenny? Is that better? Or were the steps you were asking for before this part? That helped. Okay, good. All right. Even though it was just a bit, but it helps some. That's what I want. All right. So now I'm checking. So this is a check. X equals 23. I'm taking it back to the original. 2 times 20, square root of 2 times 23 plus 3, minus the square root of 23 plus 2 equals 2. 23 times 2 is 46. 46 plus 3 is 49. 23 plus 2 is 25. Square root of 49 is 7. Square root of 25 is 5. 7 minus 5 equals 2. That checks. How about negative 1? I'm going to check is x is negative 1. That is the square root of 2 times negative 1 plus 3. If you're trying to figure out what I'm doing or where I'm coming from, I'm just taking the solutions that we found and plugging it back into the original. So there's the original, which is why I brought it. So there's the check of 23. I'm going to come over here to the side and check negative 1, just so I don't keep going to the right. And so just plugging in, all I'm doing is plugging in negative 1 for x. 2 times negative, square root of 2 times negative 1 plus 3 minus the square root of negative 1 plus 2 equals 2. You can probably start to feel how this is going to go. 2 times -1 is -2. -1 plus 2 is 1. -2 plus 3 is square root of 1. Square root of 1 is 2. The square root of 1 is 1. 1 minus 1 is 2. 0 equals 2. That is not true. So that fails our test. So that means my solution set contains 23. And that is it. All right. Questions? Probably, right? All right, so what I want to do is I'm going to step out. I want you to do this. The next page is practice. I want you to tackle this problem on the left. Okay, I want you to tackle the 3 plus square root 3x plus 1 closed quantity equals x. Okay, I'm going to give you 5 minutes. I'm not going to take any questions because I want you to think and I want to see if you're comfortable. If you finish this one in the next 5 minutes, start to tackle the one on the right. It's a little more difficult. All right, so give that a shot, and then we'll come back in 5 minutes. Okay. All right, so I'm just quietly going along. Plugging in. So did we all come up with 8 and 1 before we checked? Okay. Yes? Oh, great. All right. So When I check 8, it works. When I check 1, you already know right here, yep, 1's not going to work because look at what I'm doing. This is 3 plus the square root of something. The square root always returns positive numbers. So I know this is going to be 3 plus something greater than 0 equals 1. 3 plus, the only way to get 3 plus something to be 1 is if you're adding a negative number. So what do I have? This is 3 times 1 is 3 plus 1 is 4. 3 plus 2 equals 1, so 5 equals 1. Nope. So my solution set contains 8. All right. Any questions? I do apologize for the not clearing the fractions because I know that did make that problem a lot easier to work with. But there are a couple ways to deal with rational equations, and we talked about that. All right. So we're not going to get to absolute values today, and that is okay. Or if we do, we're going to get there very briefly because I want to show you a radical equation, but it's not given or it's not obvious that it's radical. Any specific questions on the work here? Okay. I promise you, I know you can't believe this, but I went to college, okay? And part of a math class was if I don't have a clue how to do this, there's nothing wrong with you can find the answers and work backwards. You can, if you can't follow this, if you can't come up with this on your own, but you see another problem that looks like it and you just start plugging in to just follow the steps, that is absolutely part of the learning process of math, okay? If that doesn't make any sense to you from scratch, but if I gave you a problem like that and I gave you a 6 instead of a 3, and a 1 and 2x instead of 3x and some other numbers, and you could mimic what I'm doing, that's the first step in learning, all right? So don't be frustrated that this all seems crazy or that it's just nothing, because the first time you see something new, it doesn't click, right? If it does click, then you probably don't need to be in this class. All right, so take heart in that. Practice really does make permanent in this class. All right, so here's that radical equation in disguise because I have fractional powers. So the rule says, and I'm just going to come over here and just a little reminder, that if I have some real number, let me do our math here. Let A be a real number, and N be a real number. I could have done that in one step. If I have A to the 1 over N, that means I have the nth root of A. So if I have a number raised to a power, and that power is fractional, that is trying to tell me to take a root of some number. All right? So for instance, if I gave you x to the 1/2, that means 2 is my root, is my index, and x is in the radical. That's a square root. We don't write the 2 typically, so this is how you would end. But if I had 3/4, let me make sure that looks like an exponent. Okay, what do I do here? Remember that this is cubed, right? And then this is the 4th root. So I'm taking the 4th root of x cubed. So what does that look like on the left? All right, so just a reminder. On the right, this is a radical. And like I said, it doesn't look like it, but let's make this transformation, okay? First thing I'm gonna do is x is in parentheses, and I have a power. I'm gonna isolate my x, whatever x is in this radical, and get everything to the other side. This 3 is on the outside, it's multiplying, so I'm gonna get rid of it by dividing it on both sides. Now I'm left with 5x minus 2 raised to the 2/3 is equal to, now instead of trying to square this and then take the cubed root, I'm going to use the same rules that we did before. I'm going to exponentiate both sides, okay? What I would love to happen is I don't want to deal with that fractional power, okay? So I need to multiply 2/3. If I multiply 2/3 by 3, once the 3's divide, I'm just left with the x, 5x minus 2 squared. Yeah, so I'm going to raise this to the 3rd power. If I do it over there, I have to do it over here. So isolate, exponentiate, and what happens? I'm left with 5x minus 2 squared is equal to 8. Right? Well, this looks familiar. Now this is the square root thing. This is the square root. I have an expression with x in it raised to a power, raised to the 2nd power, is equal to 8. I would like to liberate x from this. So what do? Take the square root of both sides. So that means I'm looking at the square root of 5x minus 2 squared is equal to the square root of 8. If you're think about this for a second. That's the same thing as raising it to the 1/2 power, isn't it? And 2 times 1/2 leaves me the power of 1, which is why I end up with 5x minus 2. On the right, I'm taking a square root of a positive real number. So I got to do both. Good question. I have to do both. Right? On the left, I squared a square root. On the right, I've taken a square root. So I need to deal with plus and minus. Let me clear up on the right one thing. 8 is 4 times 2. Does it have any factors that are perfect squares? Absolutely. 4 is a perfect square. The square root of 4 is 2. I'm going to do this. This is more steps than you need to show. If I have the product of a square root, I can bust that up into the products of square roots. Square root of 4 is 2. So that becomes 2 square root 2. Okay, that is one number. Doesn't look like it, but it's one number. All right, and now I want to solve for x. Okay, so what do? I want to get x by itself. I'm going to add 2 to both sides. So what do I have now? I have 5x is equal to, I'm going to put the 2 out front because that's easier to deal with that plus minus. And then I'm going to divide both sides by 5. And I end up with x is equal to 2 plus or minus 2 square roots of 2, all divided by 5. Does this simplify? A little bit. The numerator, both of those terms have a 2 in it, so I could factor it out. That's going to give me 1 plus or minus the square root of 2, all divided by 5. And then for my solution set, if I do the solution, or this breaks down into 2 numbers, this is either 2 times 1 plus root 2 over 5, or 2 times 1 minus root 2 over 5. which can also be written as, these are the exact same numbers. I'm just showing you. I just want to show you how notation can make the same number look like they're different numbers. Okay. Then you have to check them. Okay. Checking that is a bit of a pain. So what I recommend is to use a calculator or Desmos to do your work, or to do this check. And the way I'm going to do the check is I'm actually going to plug in my original equation. And I'm on the wrong page. Here we go. So what was the original equation? The original equation is, so I've got a left-hand side, 3 times 5x minus 2 raised to the 2/3. And the right-hand side of the equation is 6. What do those look like? Oh, my view is way off. There, we're going to take this back to home. $100. There we go. All right, so here is the 3 times quantity 5x minus 2 plus quantity raised to the 2/3. What does just 6 look like? Well, that's just a vertical line. Or excuse me, yeah. If I graph 6, what does this look like? Okay. Where is x equal to 6? X is equal to 6 right here. This is vertical line. What I'm looking for is, remember, what did I start with? I started with this equation, 3 times quantity, 5x minus 2 closed quantity raised to the 2/3 is equal to 6. So the left-hand side of the equation is my green graph, the right-hand side is my blue graph. And when equations, I'm testing or I'm looking for, when are these two things equal? When are they equal? They're equal when they intersect. There's only one intersection, so it tells us that one of the roots is good, one of them is extraneous, and you can check it, and it turns out that the solution for the question is just the plus. The minus doesn't make the cut. So this checks, this fails. My solution set contains 2/5 times 1 plus root 2. All right. So that is radicals. Let's just stop there for a second, because I do want to talk. We only got through 3 pages of notes today. That's fine. But would everybody be okay if we're recording these now, if I make the videos, if I make some lectures that you should watch outside of class? Because I'm supposed to have you for another 50-minute period, but I don't, because the lab section's online. So if I started making videos for this class and then asked you to watch them before we come to class, would everybody be good with that? Again, you can watch them anywhere. Would everybody be willing to do that? Yeah. Well, so you would have them to review and look over, and then the beginning of class after, I would absolutely open it up to questions. So if you run into anything, Oh no, you don't have to watch. You can watch them anywhere. So I'm going to post them on. I'll post them on YouTube and on Loom, so you would be able to watch them. You can watch them in the afternoon. You can watch them at night. You can watch them on your phone. You can watch them anywhere. So it wouldn't be a you have to do this directly before class. You could do this anytime, even during the weekend. So, okay, yeah. So if we do that. And then what that'll do is anytime I have I always like doing a long problem with the class, or at least showing you the steps all the way through. And the time just doesn't work. The amount of time we have doesn't work for us. So I like it. I want to do it, but this is the only way I'm going to be able to. So I'm already doing examples in videos that are supplementing the lecture. So if I just start making up some just like page 4 to page 6 lecture. I won't make any videos that are more than 15 minutes long. And then they'll be titled based on the page numbers from your notes. So it'll be, this is the next page here, solving absolute value equations. So it'll be solving absolute value equations, R.5, part 2, page 4 through probably 4 and 5. Or whenever I hit 15 minutes, I'll stop. And then I'll just pick it up and do, page 5 and then page 6. And then they'll always be there for you to review, right? They won't go away. So if you miss class, this also would help if you miss class, if I do a lecture. And then if I ever get caught up on anything, maybe I can have some video lectures of content, future content, ready for you so you can start exploring if you want. All right? So we're doing good work. These problems look nasty. I'm fully aware of it and I know it, but I also want to show you this is expected knowledge. Okay, this is stuff that would have been done, maybe not into the detail that we're doing it, but most of the process or concepts here should already be in your toolkit. Now, can you do them still from whenever you learned them? Maybe, maybe not. But most of this is prior knowledge. Again, here, what did I do? The whole thing was introducing this idea of fractional powers. I got rid of the fractional powers right there. And now this is a take the square root of both sides, solve for x. So that's the new part. Yes, you're good. You're good. So if there's anything else, if you have questions, absolutely email them to me. And I will see you all. Enjoy the long weekend. I will be out of town. For tests, we'll be allowed to plug in a separate webcam. I think so. Yeah, as long as it'll work. Give it a test. All right. All right. We all have a good day. If you run into anything, don't be afraid to send an email and ask. And I will be out of town, so I'll be back on Monday. So if you don't hear from me, it's because I'm up in DC. All right? Equation here, because I've got the equal sign. Not just an expression. And I can't make it any larger than that right now, but I think you can see that. So solve for y, and I'm looking at 6 minus 1 over quantity at y plus 1 equals negative 6 over quantity 1 minus 1. When I've got rational equations, there's 2 ways to attack, and those ways are either get a common denominator and solve, or get the common denominator and then clear the fractions. So 6 over y minus 1. What is my LCD here? The LCD, this anytime I got a number just by itself or a variable by itself, you can always rewrite that as itself over 1. The LCD is made up of all of the factors of all of the denominators. If they repeat, they only get counted once. If they appear once, they get counted once. So I have the 1 times the y plus 1 times the y minus 1. 1 out front doesn't do anything for me because 1 times anything is 1, or 1 times anything is itself. So there's my LCD. So on the next step, I'm going to multiply both sides by this. I'm not going to multiply this out. I'm going to leave it as y plus 1, y minus 1. And the reason is the whole goal of this is to get rid of fractions. If I multiply this out, then distribute, well, I'll have created a whole new set of problems. Then I'll have to factor back to where we were. So if I distribute y plus 1 times y minus 1, that's a minus 1. If I distribute that to the problem, minus 1 over y plus 1 equals negative 6 over y minus 1, whoopsie, times the LCD. Distribute y plus 1 times y minus 1 times 6 is just 6 as y plus 1 times y minus 1. Y plus 1 times y minus 1 times 1 over y plus 1. Is everybody cool with that step? If I multiply, if I distribute the LCD, those y plus 1s are going to divide away. So I have no fraction anymore. And then I just have 1 plus whatever's left. Well, what's left? The y plus 1 divided the y minus 1 is left. So that's where that's at. Equals, and then on the other side, this is a negative. If I multiply by y minus 1, y plus 1, y minus 1, the y minus 1s divide. So I'm left with negative 6 times y plus 1. All right, now I'm going to multiply. I'm going to do this step first because these are conjugates. So I know whenever that happens, I get that difference of perfect squares. Y squared plus y minus 1. Where are the questions coming in? Wouldn't, let's see, you put a extra set of parentheses for the 6. You can, I understand now, yes, you could, but this is negative 6, it's not minus 6. And the only reason we know that it's negative 6 and not minus 6 is because there's no number sitting in front of the minus. That's what makes it a negative sign instead. You can put a parenthesis here, and that is absolutely valid. And then it's going to be distribute on that side just the same. Next step, distribute that negative, and then on the right, distribute the negative 6. All right, see if I can put this off to the side here so I can keep up with the questions. Here we go. At the beginning on the left, again, you could do that. You could put a parenthesis here like that, and it's not wrong, but it's, since it only has one factor in it, it's not a binomial, trinomial, or anything with multiple terms, the parenthesis isn't necessary, because when I put the 6 right beside the parenthesis y plus 1, that means multiply the 6 times the whole parenthesis, or everything inside the parenthesis y plus 1. Now, the next step, distribute that 6. Now, how's that going to impact my answer? Left side, distribute the 6. If you distributed the 6 before you did that, what would you get? 6y plus 6 times y minus 1. Let's come out here. Yeah. 6 times y plus 1 times y minus 1. Okay, yeah. All right, so we're good there. This multiplies the difference of perfect squares. We distribute the 6. And then what? The goal is to solve for y. This is a second degree polynomial. It's a quadratic because the highest degree of the variable is 2. Whenever I have one of these situations where I've got terms on the left and the right, first thing I'm going to do is clean up both sides, combine all like terms on each side before I start moving stuff. Okay, so 6y squared is 6y squared. Negative 6 minus y plus 1. Negative 6 plus 1 I can work with. Negative 6 plus 1 is negative 5. On the right, there's nothing to do. Okay, so now I have on the left and right, I have a single term for the second degree term. I have a single term for the first degree term. I have a single term for the constant. On the right, I don't have a second degree term. That is fine. I have one term for the first degree and then one term for the constant. Does everybody understand that concept, the way I'm saying it, when we're saying one, that I only have one term that has y squared in it, I only have one term that has y in it, I only have one term that has a constant in it. I want that to, when we're teaching, we're kind of like comedians, we're kind of testing out new material to make sure if maybe we can stumble upon something that really makes sense. So I'm going to move everything to the right, which means I'm going to add 6y and add 6 to both sides. 6y squared, there are no like terms that were brought, so that's just 6y squared. Negative y plus 6y, it's 5y. Negative 5 plus 6 plus 1 equals negative 6y plus 6y is 0. Negative 6 plus 6 is 0. Excellent. So now I have a quadratic, and I would like to solve it. Okay, so Tinny, this was yours. How would you like to solve this part? Did that get you to the part you can solve it, or do you want to keep going? Is there a way you want to do this part specifically? Yes, yes, we can. So let's come over here and do that. So 6y squared plus 5y plus 1 equals 0 becomes y squared plus 5y plus 6 equals 0. Does this factor? Absolutely. Two things and multiply to 6 and add to 5. I'm multiplying to a positive 6 and I'm adding to a positive 5. My first thought was 6 and 1, but that doesn't work. But 2 and 3 does. And they're both pluses. Now, don't forget the step. Remember what we did here. We took A, multiplied it by C, so back, and divide my constant term from my binomials by what the old A value was. Do they reduce? And now we can come back and deal with this problem. Y plus 2 over 6 is the same thing as y plus 1 over 3. Y plus 3 over 6 is the same thing as y plus 1 over 2. And so here's the thing. This says solve. What I taught you, or what I showed you in the past, was bring the denominator of the constant out front, but you don't need to do that. I have two things to multiply to give me 0. You only had to do that because the question asks you to factor but not solve. In this one, we're back to our friend by the zero product principle. If two things multiply to 0, oops, one of them is 0. So y plus 1/3 equals 0. Y is equal to negative 1/3. Y plus 1/2 equals 0. Y is equal to negative 1/2. So those are my two answers. And question is, do they work, or either of those solutions? Okay. So first thing I'm going to do is I'm going to take a glance. Let's look at our original problem and see what are the values of y that would cause division by 0. Y cannot be. What value of y would make this denominator 0 in the second term, that y plus 1? Y cannot be negative 1 or 1. So I don't have any extraneous solutions appearing like that. But let's check. How would I check this? I would go to Desmos. And plot the left-hand side of the equation and the right-hand side of the equation. So here's the original. Left-hand side, 6 minus, 1 divided by parentheses, y plus 1. And, oh, I forgot, Desmos doesn't like to play games only with when you don't have x. X minus 1. Now, this is the left-hand side of my equation. Everybody agreed with that, except for obviously it's x instead of y. The blue line is the equivalent of, it is the expression on the right-hand side of the equation. X and y are swapped. What's going to make this statement true? What are the values of y where this curve, this expression on the left and this expression on the right intersect? Where do they intersect? Well, it looks like they intersect right here. That's negative 1/2. And that's negative 1/3. Thoughts on that? Better? Okay. I saw another question. Sadie said question 4. And that was the same section. R6, okay. Let's get over to it. R6, question 4. May not have tackled this yet. Okay. A model rocket is launched with an initial upper velocity of 202 feet per second. The rocket's height in h after t seconds is given by the following. Find all the values of t for which the rocket's height is 82 feet. Round your answer to the nearest hundredth. That is possible without the absolute values. So let's take a glance at this. Oh yeah, we haven't covered that in the notes, so yes, we will talk about the absolute values. All right, so Steven, did I get you? Oh no, don't worry about those objectives. I'm going to move those dates. It's just they're today, but they will move. So you don't have to worry about that. I'm not going to make you do something in R6 if we haven't covered it. All right, so R6 question 4. Here's the rocket. It's launched with an initial upward velocity of 202 feet per second. And rocket's height h in feet after t seconds is given by the following model. The numbers should look familiar here. H is the height off the ground. 202, that's the initial velocity. And then it is sitting beside t, because after 1 second, the rocket launches with 202 feet per second of velocity. So after 1 second, it should have traveled 202 feet. After 2 seconds, it'd be 404, and so on and so forth, except we have gravity. This second term right here, that negative 16t squared, that is gravity, okay? That's gravity at work. It's bringing the rocket or pulling the rocket back down. It is slowing it down. And that's why we need a quadratic here, because rockets don't shoot off in a line and then reach the top and then fall straight down. They go up, they reach their peak, and they kind of tip and fall over. So question is, when find all the values for t where the rocket's height is 82. Well, the rocket's height is this equation. H of t is equal to 202t minus 16t squared. Okay, so this is just the name of the function. This is the height. The height. And I want to know to do what? Find t when h of t equals 82. H of t, this is going to return the height after t seconds. So after 0 seconds, the height hasn't left the ground, the rocket didn't leave the ground, this side would return 0. After 1 second, it would be 202, except gravity's pulling, but that's fine. So what does this mean I need to do? I have 82, and 82 gets plugged in to the h of t. So that whole side is 82. On the right-hand side, I have the remaining terms to make a quadratic equation. And now all I have to do is solve that quadratic equation. So let's get everything on a side by itself. This is a quadratic. It means subtract 82. No like terms on either side. Nothing to add or subtract left or right. So I have 0 is equal to, I am going to write this in descending order, 16t squared, negative 16t squared plus 202t minus 82. Okay. Okay. And now it's a problem. Now it's a problem you know how to do. Right? That's quadratic. How would you tackle this? Okay. First thing, quadratic formula. We're going to end up there. First thing, we have common factors. Everything is divisible by 2. So let's see if I can make my problem a little easier by using smaller numbers. Minus 41. Anything else left in common? What I did there technically is I factored a 2 out and then divided both sides by 2. 0 divided by 2 is 0. So that's why I didn't just make that go away. Negative 8t squared plus 101t minus 41. Quadratic equation sounds good to me.
Our quadratic formula sounds great. So quadratic formula says t is equal to the opposite of b plus or minus the square root of b squared. B is not -8, Larry. B is 101 minus 4 times -8 times -41, all divided by 2 times a. Okay. So that goes into a calculator because, and I know I don't have to solve this one and I don't have to get this in radical or rationals, because the question says round your answer to the nearest hundred. So that's a clue that when I do all this, when I do all this work, all I care about is when I get to the end, do I have, what's my number? So rather than do that, let's just go right here to Desmos, and let's let it do that for me. -101, because this also does numbers. -101 plus square root 101 squared minus 4 times -8 times -41 divided by 2 times -8. Oh, I got a slash in there behind that square root symbol. So there's one of them, right? So that's the equation. That's for when this is a plus. What is it for a minus? Well, I'm just going to copy. I'm going to paste, and then just switch that plus for a minus. And here are our answers. Rounds to the nearest 10th, 100th. All right, to the nearest 100th. Those numbers are 4199, blah, blah, blah. So 10th, hundredths, that's two places. So 0.42. These are seconds. And the other one, 12.20, which to two places is going to be 12.21. And you really don't need to write that twice. We have our values here. Units are absolutely necessary because it's an application problem. If you tell me t is 0.42, that's not enough. Number 7 on the R5. Good. Number 7 on the R5. R5 part 1 or R5 part 2? Olivia, which one? Part 1 or part 2? Part 1. Part 1. Number 7. Same game. So this is very similar to when we did. I'm actually going to, instead of putting that page over here, I'm going to put it in this new one. This is R.5 Q7. I'll set it up and then you'll have access to it. I may not finish it all the way out. All right, so here's the problem. And we're looking at the same situation we had before. The difference here is the numerator and denominator are binomials. Did I miss something? Oh, that's a different question. R5 part 1. 6, 7. How is it? This one? Maybe the one with the squares, or not like this at all. Okay. All right, if you find it, send me the number. Oh, okay. Question 7 is the same form as social work. Okay. All right. So, yeah, and this is going to have that similar format to the one above. Y plus 4 over y minus 2 is equal to y plus 3 over y minus 1 plus 1 LCD. Y minus 2 times y minus 1 times 1, because that's really got a denominator of 1, but 1 times anything is what I started with. So I'm going to multiply both sides by the LCD. I'm going to leave it in factored form. So that way the division occurs that I want, and I get the fractions cleared. Minus 2, y minus 1, distribute, y minus 2 is divide, so I'm left with y minus 1 times y plus 4. On the right, the y minus 1's divide, leaving me y plus 3 times y minus 2, plus y minus 2 times y minus 1. So I have 3 multiplications to do. Y minus 1 times y plus 4 is y squared plus 4x minus, or excuse me, y squared minus 1x plus letters. Why are letters so hard today? 4y minus y is 3y. Negative 1 times 4 is negative 4. On the right, y times y is y squared. Y plus 3y plus 2y is 5y. 3, just about got in trouble. What are you doing, Mr. Tingen? First, outer, negative 2y plus 3y. Gives me single y. And then 3 times negative 2. It's negative 6 plus, I don't have parentheses around this result. I can do this. That's going to be y squared minus 3y plus 2. And the reason I would do that is it's not necessary, but it's good practice, because if there were subtraction going on in the problem between these products, the subtraction would need to be distributed. So since the problem started with a plus, the only add subtract in here is an addition. I don't have to distribute the plus, but you can see why I've got the parentheses around them. Now, we know they factor because we just put them together. I don't want to factor them. I want to solve. So this is, I got 3 quadratics. On the left, I have a single term for y squared, a single term for y, a single term for the constant. On the right, I have 2 of each. So let's clean up the right-hand side. Y squared plus y squared is 2y squared. Y minus 3y is minus 2y. Negative 6 plus 2 is negative 4. Now, one term on each side. I need to move everything to one side. I don't like dealing with quadratics when the leading coefficient is negative. So that is gonna, my instinct here is to subtract everything off the left-hand side. The only reason really and truly is, or just remove everything from the left-hand side, is because when I do this step, on the left I have 0. On the right, 2y squared minus y squared is y squared. If I had subtracted 2y from both sides, I would be dealing with a negative y squared. And I just don't like leading coefficients that are negative, because then the next step is to flip everything. Negative 2y minus 3 more is negative 5y. Negative 4 plus 4 is 0. Ooh, that's a great result. Love it. Because what have I got now? I don't have a constant term, but on the right-hand side, I have a second degree term and a first degree term for y. They have a common factor of y. Right? And then by the zero product principle, I know that if two things multiply to give me 0, either y is 0 or y minus 5 is 0, which means y is 0 or y is 5. Now, check. First thing I'm going to do is check for the extraneous solutions. So I'm going to go back up to my original. Do I have any issues? What are the values that are not allowed? Y cannot be, what? If it's 2, 2 minus 2 is 0. That'll cause division by 2. So I can't have a 2, and I can't have a 1. Are 2 and 1, 2 or 1 one of the solutions? No, they're not. Okay, great. So I got 0 and 5. And now let's go back to the original, plug them in. You can do it like we did with Desmos, and see what you get. And I'll leave that. Leave the check for the reader. As you get farther into math textbooks, this is like a famous phrase that we all like to say. Something like the process of doing this is so simple, I leave it to the reader. So if you ever see that, that's what they're doing. All right, so we're refreshed. We're back up to pace. We've seen our last thing we saw was our radical equation in disguise with our fractional powers. We got introduced to our solution sets, and then the last thing in R5 part 2 is solving absolute value equations. So this is page 62 and 63 if you want to reference it. I want you to think about what is an absolute value. The box to the right has the definition of the absolute value. And this is called a piecewise function. Okay, and what that means is for certain values of whatever the variable is, we do one thing. For certain values of the variable, we do something else. So given k, given a non-negative real number k, the generic absolute value equation, the absolute value of u is equal to k, can be solved directly from the definition below. The absolute value of u is u if u is greater than or equal to 0, and negative u if u is less than 0. That feels backwards, doesn't it? Doesn't feel like the way we dealt with it. So let's go over here to the left and tackle some of these questions. What values of n make the absolute value of n equal to 5 true? Well, what makes n, absolute value of n is equal to 5? What makes it true? Well, when n is 5 and when n is negative 5, right? Because I'm going to take the absolute value and I'll end up with 5 equals 5. What about what makes consider what values of n make the absolute value of n equal to 0? Absolute value of n is 0. That means that n must be, okay, Now, I used to try to trick my students into say that there's obviously a positive and a negative 0, and then I found out that people don't get my sense of humor and that that's not funny. So I stopped saying it because there is no such thing as a positive 0 or a negative 0. 0 is neither positive nor negative. It is neutral. So the only solution for that is 0. On the last piece, what values of n make the absolute value of n equal to -5? None. Because look at the absolute value equation. What does it always put out? It always puts out positive answers. Right? And there's our rundown. There's just kind of the rundown, the cardinal rules here. If the absolute value of u is equal to k, solutions are k and negative k. If the absolute value of u is 0, that's equivalent to u is 0. If the absolute value equals negative k, this is where we know that k is a positive number, so putting a negative in front of it means that that whole side is negative. This can't happen. Absolute value cannot be negative. And then lastly, we have a case where I have two variables. Absolute value of u is equal to the absolute value of w. That's equivalent to saying u is equal to w or u is equal to negative w. So what we do is we leave one side alone, we turn the other side into a plus minus. So let's tackle it. And then first off, we'd already mentioned this, and I know some people had already talked about it. Just remember, absolute value is distance from 0, right? The absolute value of 5 is 5 because 5 is 5 units from 0. So if you ever just need to go back and start with the basics, draw a number line, find the number you're looking at, count how many times it takes you to get to 0. Doesn't matter if you go left or right because it's distance, right? It takes me, I think my office is 19 miles from my house. It's 19 miles to my office, and then it's 19 miles from my office home. It's not 19 one way and negative 19 one way. All right, distance is always positive. So let's solve this absolute value. Absolute value 1 minus 4t closed absolute value is equal to 5. So which one of these four cases do I have? I have the absolute value of some expression u is equal to some positive real number k. All right, so this is situation 1. So what does it say I can do? I can break this into 1 minus 4t is equal to 5, or 1 minus 4t is equal to -5. Notice that no math was done in that process of dropping the bars. No math was done in dropping those absolute value bars. The only thing that happened was I was able to use this property. If I have the absolute value of something equals a real positive number, then the result must be 5 or -5. Solve each one of these. Everything, so these are linear because the highest degree of the variable is 1. So everything with variable on one side, everything without on the other. Subtract 1, subtract 1. -4t is equal to 4. Divide by -4, divide by -4. T is equal to -1. T being -1 is fine because I can put a negative number inside the absolute values. What I cannot do is have a negative number as an answer of an absolute value. All right, how about my other problem over here? Same steps. I want to get everything with a t on one side, everything without on the other. -4t is equal to -5 minus 1 more is -6. T is almost by itself. It just needs to be divided by that -4. And I'm left with t is equal to 6 over 4 is 3 over 2. A negative divided by a negative is a positive. All right, so my solution set is -1 and 3/2. Questions? Anything? Okay. So let's tackle the next one. The biggest temptation when solving absolute value equations is to try to put some math or do some math inside the absolute value bars. As long as absolute value bars are in the problem, you can't do anything with the values inside. For instance, the next one has x squared minus x inside the absolute value. I'm not going to factor an x out of that and get x minus 1. The x times x minus 1. I cannot do math while I have absolute values. What I need to do is follow my steps. And my steps are isolate the absolute value, separate by breaking it into either what's in the absolute value is equal to positive k, what's in the absolute value is equal to negative k, and then liberate the variable out of the absolute value so that we can do some math with it. So for this one, I can't just, I can't say, oh, well, this is 9 and negative 9, because step 1 is isolate. Right, my rule says if k is a real positive number and the absolute value of k is equal to u, then u is either equal to k or u is equal to negative k. Right? That means positive real. There's the double barred R for real, and that just means positive. So do I have that yet? No, the rule says I have to have just the absolute value on one side. So if I want just the absolute value on one side, that means this minus 3 needs to go away. I can do that. I can do that by adding 3 to both sides. So what do I have? I have x squared minus x equals 12. Now do I have the absolute value of some expression of x is equal to a real number, a real positive number? Yes, I do. Now I can use that property. So that means either x squared minus x equals 12, or x squared minus x equals negative 12. Notice the sign is always changing on the real positive number, not on the side with the variables, not on the side where the absolute value was. Okay, and let's go. Okay, both of these are quadratics. How are they going to work? Well, they're quadratics, so I need everything on one side. So subtract 12 from both sides for the one on the left. Two things that multiply to negative 12 add to negative 1. If I'm multiplying by a negative, that means this is plus minus. And the fact that this is a negative 1 means the negative number has the highest magnitude. Two things multiply to give me 0. So that's 0 product principle. X plus 3 equals 0, or x minus 4 equals 0. X is negative 3, or x is 4. What about my other one? Minus x plus 12 equals 0. Two numbers that multiply to 12 and add to negative 1. That doesn't seem familiar. I know they don't exist because I'm multiplying to a positive. So that means my values are both negative or both positive. And then that middle coefficient b is negative 1. So that means if this factored, it would be x minus something times x minus something. There are not two numbers that multiply to 12 and add to negative 1. So I cannot factor this one, but I can use the quadratic. I can't use bottoms up because my leading coefficient's not, it is 1. So all I can do is break this down. The opposite of b, plus or minus the square root, b squared minus 4 times a times c, all divided by 2a. Negative 1 is 1, plus or minus the square root. Negative 1 squared is 1. 4 times 1 is 4. 4 times 12 is 48 over 2. And suddenly, we have an issue. 1 minus 48 is negative 47. Negative 47 doesn't scare me. Negative 47 under an even root does scare me. Negative under an even root means the solutions are complex. What that means is this is where I comes back in. And you've heard of the square root of negative 1. So that means for this problem, what do I have? Well, the problem itself, it needs to tell you which kind of solutions you're looking for. Are you considering these for all real numbers? Or are you considering these for complex numbers? If you're considering for real numbers, we toss this answer on the right. If we're considering it for complex numbers, we use both, this negative 3, the 4, and then the result. So let me finish this. I'm going to do this step right here. Negative 1 over 2 plus or minus the square root of, is everybody cool? This little piece right here. Negative 47 is negative 1 times 47. The square root of negative 1 is I. So this becomes 1/2 plus or minus I square root 47 over 2. All right, so you do have 4 solutions to this original inequality, to this original absolute value equation. We need to check them though. Do they work? Negative 3, positive 4. Let's take a look. So the original is absolute value of x squared minus x minus 3 is equal to 9. So let's check our real answers first. I'm going to ignore the complex solutions for a little while because we weren't directed to use complex solutions. And when that happens, we just pretend like we just say there are no real solutions. Negative 3 squared is 9. 9 minus negative 3. Oops, I got ahead of myself. Minus negative 3 is plus 3. You can probably already see this is going well. Absolute value of 12 minus 3 is equal to 9. Absolute value of 12 is 12. 12 minus 3 is 9. 9 equals 9. That checks. How about 4? Okay. So that's 4 squared minus 4 minus 3 is equal to 9. 4 squared is 16. 16 minus 4 is 12. So the value of 12 is 12. 12 minus 3 is 9. 9 equals 9. That checks. So my real solutions are negative 3 and positive 4. Now, you saw on the graph earlier, when I wanted to check if there were answers, I could plot the left-hand side of the equation, the right-hand side of the equation, and look for the intersections. These are the numbers that would show up on a graph. Complex numbers don't show up on that Cartesian plane. Okay, they don't show up in those situations. So we'll get more into that later, but for now, right now we're going to ignore that they're complex solutions until we're told directly to start dealing with them. Does anybody have any questions on this? All right. So if not, I am exhausted I cannot continue going. So I'm going to leave these two problems up. I want you to take the next 10 minutes, talk amongst you. Let's see, -2 or 3. Okay. And then you check.
Oh, of course. Yeah, that's me. I can absolutely help. Please pull your account so we can get that scheduled for you.
All right, so -2 checks.
That's right, and really, it's just a precautionary measure because it's the last course to take in your major, and it's literally just set up this way so that students don't sign up for it before they're supposed to. You can go to birthday, Justin?
Yep.
And I'm just gonna do a brief check to make sure everything in your major is completed.
Good.
I'm pretty sure you're just fine. And what?
All right. All right, So once you're comfortable with that, you can call it a day.
Yeah, that's fine. Yeah, because those are scheduled, we can go ahead and set this up. I'm assuming, do you want this for the winter